Okay, hello. This is like the seventh time I've tried to record this and something goes wrong every time. So this time I have my sound on, my video on. I've been through the problem like 7 times that I should be able to get this done for you. So let's talk through number 53 in section 2.9, get to work on the whiteboard, shall we? So let me get where I can write and do number 53 for you. So I've got the notes once again in Blackboard under course content, kind of stepping this out. But basically number 53 in section 2.9 is looking at the Statue of Liberty and a plane flying over the top of Our Lady here that's got the flame of American independence and her crown, and flying above that crown is an airplane that is going at a speed of 4.5 kilometers per hour. So we're going to call that going to the right as being positive, that's the X direction, going up as being positive, that's the Y direction, and that plane is flying 2 kilometers above her. And the question is, for the line of sight for the Statue of Liberty, what's the rate of change of the line of sight for her? So let's look at a couple of things that we do, and this is 20 seconds later. So instantaneous rate of change of the distance away the plane is moving with respect to time. So let's look at a couple of things that we know. First of all, it says the speed of the plane was 4.5 kilometers per hour, not per hour, sorry, per minute, going to the right or the positive direction. So, of course, one thing that we could do is we could actually figure out what X is, because X would be the distance after 20 seconds. So 20 seconds is the same as 1/3 of a minute, right? So T equals 1/3 of a minute. What would X be? Well, distance equals rate times time, or some people prefer to put TR because that's my initials, Tim Ryle. But anyway, times rate. But anyway, rate times time is 1/3 of a minute. Time is 1/3 of a minute times the rate, which is 4.5 kilometers per minute. And the minutes would cancel and you're left with kilometers. So this ends up being 1.5 kilometers. So that's how far the plane is to the right. So X would be 1.5 kilometers to the right after 20 seconds. And of course, we could call this Z here. So this third side, we could call Z for the variable. That's going to be changing as well. But we could use Pythagorean's theorem and say, hey, X squared plus Y squared is Z squared because we have a right triangle. And if we do that, this is actually a 3, 4, 5 right triangle relationship. So 1.5, 2, and then Z would actually be 2.5 kilometers. So like, 15, 20, 25, or any 3, 4, 5 ratio would work out. So this actual distance is 2.5 kilometers, but that's not the question. The question is, what is the rate of change of the line of sight with respect to time? Well, that's dz dt. So how is the distance with respect to time changing on that line of sight? So that's what we're trying to find. So to do that, let's just take the instantaneous rate of change of this equation, which we know we have with respect to time. And so with this, I'm taking it with respect to time, so the variable is t. Notice that x is really a function of time. X is really like x of t because x is going to get bigger as time increases, assuming you don't run out of gas, right? So we can take the derivative of this, and we're going to get 2x, act like it's okay. So I'm going to take the derivative of x squared, get 2x. But because I took the derivative with respect to t, not x, by the chain rule, I have to attach a dx dt. And then I'm going to keep going. Derivative of the sum is the sum of the derivatives. So this would be derivative of y squared is 2y. Once again, that y is not the variable t, so I got to attach a dy dt by the chain rule. And that's going to equal 2z times the derivative of z with respect to t, because z is also a function of t, function of time. So we have all this. Of course, we have things that we can plug in. So this X we know to be 1.5 kilometers. Dx dt we're actually given. So that is the speed, and it's positive. So it's going to the right. So it's a constant rate of change, but it's also the instantaneous rate of change of speed. So dx dt, positive just means moving right, but is 4.5. We can plug that in. So we have that. We know that y equals 2. And we know that z equals 2.5. So we have everything except for what? Everything except for dy dt and dz dt. Of course, we're trying to solve for dz dt to actually figure out the solution. But the question is, what is dy dt? Well, if here's how far the starting point for the height difference, but down the road after so many seconds or minutes, excuse me, this y's height is still going to be 2, no matter how far the plane goes to the right until it starts running out of gas or the wind changes or something else is affecting this problem. The rate of change of height with respect to time is actually 0. So that kind of makes this easier to solve, because this whole thing, this whole product here becomes 0. So really what we have is we've got then 2 times x is going to be 2 times 1.5 times dx dt is 4.5 kilometers per hour. Plus 0 is going to equal, on the right here, we've got 2 times z, which is 2.5, and dz dt. And dz dt is what I want to solve for. Of course, if I multiply on the left, I'm going to get, I could cancel out the 2's, but it's a little bit easier to multiply with them in there. So 2 times 1.5 is 3. 3 times 4.5 is 12, plus 1.5 is 13.5. So I'm just going to clear this and go back and keep writing. So I've got 13.5 on the left side of the equation, and that equals, it was 2 times 2.5, which is 5 times dz dt on the right side of the equation, trying to solve for this. So I'm going to divide both sides by 5, and of course, dividing by 5, let's go ahead and divide it by 10, and I get 1.35, and then double it. So that's 2.7 is going to equal dz dt. Now, of course, we always want to label this, but what is rate of change of z? Z is a distance, right? So the distance is measured in kilometers, and change in time, dt, is change in time. That's being measured in minutes. So, and of course, this is a positive result here. Well, what does that mean? So the way we interpret this is that the line, so dz dt is the line of sight from the Statue of Liberty to the plane, and since it's positive, is the rate of change of the line of sight is increasing at a rate of 2.7 kilometers per minute at the point in time that you're 20 seconds or a third of the minute into the flight. So anyway, there we go. That's an explanation of the notes that I have. So if you've got other specific questions or other odds that you're having struggles with, or specific questions on your evens, utilize that WhatsApp or reach out, and good luck, and I'll see you soon.